Alright, so the first problem that we've got today is a simple vapor compression refrigeration system operating between the pressures of 100 kilopascals and 1400 kilopascals, and we have a cooling load of 1000 kilowatts. So we're looking for how much power is the compressor going to consume, how much heat needs to be rejected, or what's the rate of heat rejection from the condenser, and what's the coefficient of performance of the system. So the first way that we'll do this is with the R134A tables from your book. So here's our simple vapor compression refrigeration system. We'll start, say, going into the compressor. That's state 1. State 2, out of the compressor and into the condenser. Out of the condenser and into the expansion valve is 3. And after the expansion valve, into the evaporator is 4. So we have heat in to the evaporator, and that's what we call the cooling load. So that is 1000 kilowatts in this case. Our compressor is consuming work. That's one of the questions. And we have heat being rejected from the condenser. We were told the low pressure was 100 kilopascals, so that we would call the evaporator pressure, and that's the pressure at 4 and 1. We also have the condenser pressure of 1400 kilopascals. Okay. So our first question, well, really the first question is, we need to find the state at all of these so that we can find the temperatures. The first question is, what's all the temperatures at state 1, 2, 3, 4? So in blue, I'm going to write some of the standard assumptions that we need to make. So this is an ideal cycle. We can assume that the fluid coming out of the evaporator is saturated vapor. The ideal assumption for the compressor is that it's isentropic. It's a reversible and adiabatic compressor. If it's isentropic, S2 is S1. The phase that we assume coming out of the condenser, saturated liquid. And across the expansion valve, the enthalpy is constant. Okay. So we can write energy balance for, actually we can look up the properties first. Let's do that. So at state 1, saturated vapor, temperature 1 is just the saturation temperature of R134A at 100 kilopascals, which is negative 26.37. Now we need temperature 2. So in order to get temperature 2, we need to define state 2. We know the pressure, but we also, now we can get the entropy. So we're going to look up S1. When we go to the table, so that's saturated vapor 100 kilopascals, Sg at 100 kilopascals is 0.95183. Okay. That's also equal to S2. So now for state 2, we have this entropy and 1400 kilopascals. We go to the tables, we find at 1400 kilopascals, and this entropy, it's superheated. So now we go to the superheated tables, and we can see that this entropy falls between 60 and 70 degrees C. It's closer to 60 degrees C. And so we can approximate T2. I get about 63.5 degrees C. At the same time, we can see we're going to need enthalpy too. we can approximate enthalpy to. I get something like 289. These two should be exact. You can get those exact values in the tables. These I approximated, so if you have a small difference there, that's okay. All right, going forward, temperature 3. State 3 is saturated liquid at 1400 kilopascals, so its temperature is just the saturation temperature at 1400 kilopascals, which is 52.4. And finally, state 4, well, we can get the enthalpy there. Enthalpy 3 is going to be HF at 1400 kilopascals, which is 127.2. Now we have the enthalpy at 4 and the pressure of 100 kilopascals. So we go to 100 kilopascals, we see that our enthalpy falls between HF and Hg, which means it's superheated. I mean, it's a saturated mixture at 4. Since it's a saturated mixture, T4 must be the saturation temperature at 100 kilopascals, which is actually the same as T1, negative 26.37 degrees. Okay. All right, next thing we're looking for is how much power does the compressor consume? So if I were to write energy balance on this compressor right here, let's say the work in plus the mass flow rate through there times H1 minus H2 equals 0. If I solve for work in, I get this equation. So I need mass flow rate H1 and H2. I already have H1 and H2, so we just need to work on the mass flow rate. In this case, the thing that's going to fix the mass flow rate is this 1000 kilowatts. So if we were to write energy balance on the evaporator, I'll do that energy balance in blue, we would get Qn plus the mass flow rate H4 minus H1 equals 0. So the mass flow rate is Qn over H1 minus H4, 1000 kilowatts over H1, 234.44, minus H4, 127.22. From that we get 9.33 kilograms per second. Now we can go back to the energy balance on the compressor and actually solve for the work into the compressor. I'll move over this one. Then it was H2, 289, minus H1, H1, 234.4. So that is 509 kilowatts. That's the work in. Next question is how much heat is being rejected? So if I treat this entire system, and then the entire refrigeration system as my system, I get the energy balance of Qn plus work in minus Q out, and this is a steady system, so it equals 0. So from that, we can see Q out is Qn plus work in, so 509 plus 1,000. You would get exactly the same thing if you took the condenser to be your system. You'd have Q out plus, negative Q out plus the mass flow rate times H2 minus H3 equals 0. Solve that, you get exactly the same thing. And the last thing we want is the coefficient of performance. That is, how much cooling do we get per unit of work into the compressor. Basically, what's the efficiency of this thing? So we got 1,000 kilowatts of cooling. It cost us 509 kilowatts worth of power. So this is 1.95 or something like that. Okay.